Here we will see a special algorithm to try to optimize the weights of the network, and these are new explorations that are done in the field just to try to explore new ways of replacing the optimization of the network. So the typical algorithm to to estimate the weights is this backpropagation. So in the backpropagation, you start with an input, go with a forward pass through the network to the very end, then you evaluate your loss, and this loss is backpropagated to all neurons, so that and to all weights, so that you can update them. And there is something unnatural in this process. That is probably our neural networks in the brain, they don't work like this. So you don't have to wait to the very end and then back propagate the gradient or whatever change throughout the whole network. So probably what is happening is a much more local optimization. So let's say that we have a positive and a negative example of two data points. So we have two data points, one is positive, another one that is negative. And then we do a forward pass of the positive, a forward pass of the negative, and then at each one of the layers we perform some optimization. And probably this is closer to how the actual neural network is, or the actual brain networks are learning. They require less memory. It is a very recent algorithm, so it has a long way to go, and for the moment it is producing worse results than backpropagation. But I think it is interesting to have a look and see how it works. So the idea is that you have to construct positive and negative examples. So here are a couple of ways of generating that. So let's say that you have two positive examples, like two numbers. Then you generate kind of random mask, and then this random mask, part of it will be taken from the 7, so 7 goes through the mask, and then the 6 go through 1 minus mask. And then with these two parts you construct an hybrid input vector, and this input vector is negative in the sense that it doesn't exist. So here is another example in which you have a number 2, and then you have the label 2, number 8, label 8. But so they are good data. But here is an incorrect data. So you have a number 5, but you say it is a number 8 in the label. So you need a way to have good data and bad data, or good data as in this example, and bad data. And then let's say that you have a layer of the network that in general they can be represented like this, and we define the goodness function of the activation as this one. So if it has a lot of energy or less energy. So now we have the two responses, one to the positive example, another one for the negative example. So the loss function at each one of the layers tries to maximize the activation of the positive sample and minimize the activation of the negative example. So we have this sigmoidal function, and then what we want to maximize is the activation of the positive minus the activation of the negative. So we try to separate positive from negative examples at each one of the layers, and as said, this is giving worse results than the backpropagation, but I think it is an interesting way to start thinking of something else, so that we can explore new ways of optimizing our networks.